Good afternoon. My name is Dwayne Brown with NASA's Office of Communications, and welcome to NASA headquarters. Today, you will hear the latest findings from NASA's Messenger spacecraft that has been studying the planet Mercury in unprecedented detail since the spacecraft's historic arrival in March 2011. We'll have brief presentations, then open it up for questions starting here in Washington, our NASA centers, the phone lines, and social media. And visit NASA social media venues, Facebook, YouTube, and Twitter. Yes, join the conversation with the hashtag AskNASA. You can also follow the mission activities and updates on the science at www.nasa.gov/messenger. Before we get into the briefings, I'd like to introduce you to today's participants. First up, Sean Solomon, Messenger, Principal Investigator, Lamont Doherty, Earth Observatory, Columbia University. David Lawrence, Messenger, Participating Scientist, the Johns Hopkins University Applied Physics Laboratory, Lower Maryland. Gregory Newman, Mercury Laser Altimeter Instrument Scientist from NASA's Goddard Space Flight Center, Greenbelt, Maryland. And David Page, Messenger Participating Scientist from UCLA. Now, before we hear from our briefers, I'd like to invite to the podium Dr. Jim Green, the head of NASA's Planetary Science Division, to set the stage for us today. Dr. Green?
Well, thank you very much, Dwayne. And this indeed is going to be an exciting press conference. You know, the NASA planetary program has an array of missions that are scattered throughout the solar system. And these are making really exciting measurements, leading to fabulous discoveries. Those discoveries increase our knowledge, but more importantly, provide us a better understanding of the origin and evolution of our solar system, for which the Earth, of course, is a member of. Today, we are here to talk about the results from the Messenger Mercury mission. Now, Messenger is one of NASA's discovery missions. It's designed to do the first comprehensive global survey of Mercury. NASA's Discovery program, which began in 1992, has initiated and flown 11 missions, and in fact, we're working on the 12th one now. Messenger has been inserted, as Dwayne mentioned, into orbit about 2 years ago and has worked absolutely flawlessly during that time period. And so, without further ado, let me turn it over to Dr. Sean Solomon, the Principal Investigator for the Messenger Mercury mission. Sean?
Thank you, Jim. It has long been postulated that on Mercury, the planet closest to the sun, there are cold, permanently shadowed regions at the north and south poles where water and other volatiles may be stable as ices over timescales as long as millions or billions of years. 20 years ago, radar astronomers announced the discovery that Mercury has radar-bright materials at its poles, as you see in the first image shown on the screen of the North Polar region of Mercury. Those radar-bright materials are shown in yellow on that image. And those materials have the radar characteristics that are best matched elsewhere in the solar system by water ice, leading to the postulate 20 years ago that these radar-bright deposits indeed consist dominantly of water ice. And in fact, where those images obtained by radar overlap the images that the Mariner 10 spacecraft obtained of Mercury with its cameras in 1974 and 1975, when it flew by the innermost planet 3 times, the radar bright deposits were seen to lie within impact craters. Nonetheless, in the 20 years since that discovery, other proposals have been made that the radar bright deposits might consist of some other materials than water ice. And there have been no direct measurements of the composition or the detailed physical characteristics of those deposits until the MESSENGER mission. Since insertion into orbit around Mercury in March of last year, MESSENGER has undertaken a comprehensive campaign of the polar regions. And the next slide shows a mosaic of images taken from the North Polar region, confirming what Mariner 10 showed us after the radar deposits were discovered, that indeed throughout the polar regions, the largest of the radar right deposits do lie within impact craters. And you can see from this image of the North Pole that the deposits farthest from the pole are concentrated on the poleward-facing walls and floor of the impact craters. The imaging that MESSENGER carried out also allowed us to delineate those areas that received no illumination from the sun at all over the course of an entire Mercury solar day. And the next image compares in red the areas that are in persistent shadow with the locations of the radar bright deposits imaged in the best resolution images obtained at the Arecibo Radio Observatory in Puerto Rico. And you can see this result, which is duplicated in the South Polar region, that all of the radar bright deposits are in areas that are persistently shadowed over the course of a Mercury solar day. This is indeed consistent with the proposal that the radar bright deposits are some kind of ice, cold trapped in permanently shadowed regions. Today, there are 3 papers that have been published online by Science Magazine, led by my 3 colleagues to my left, each one of them, that present 3 new lines of evidence that it is water ice, indeed, that dominates the composition of the polar deposits on Mercury. One of those papers deals with measurements of the flux of neutrons in the polar regions. One of those papers deals with the active measurement of the reflectance of Mercury's surface. And one of those papers deals with new models for the temperature of the surface and near-surface regions near the North Pole, determined on the basis of measured topography that has been obtained by the MESSENGER spacecraft. The next slide shows that obtaining these measurements has not been easy and it has not been quick. The MESSENGER spacecraft for 13 months was in a 12-hour orbit. The orbit is not strictly polar, and it is highly eccentric. And even at the highest latitudes reached by the MESSENGER spacecraft, the vantage point is anywhere from 250 to 600 kilometers off the surface. And moreover, the spacecraft must look at an oblique angle to see the very highest latitudes. Since April of this year, MESSENGER has been in an 8-hour orbit, but it's still at very high altitudes, 250 to 400 kilometers off the surface at its highest northern extent. Despite the challenges to obtaining these measurements from these 3 different methods, as you will see momentarily, the 1.5 years of observations that MESSENGER has completed have now finally yielded very clear results. And for the first of those results, let me turn to my colleague on my left, David Lawrence.
Okay, thank you, Sean. And so for this part of the story of this 20-year story that we have of ice at the poles of Mercury, I will be presenting results of hydrogen concentrations at the North Pole of Mercury. And by measuring hydrogen, we can infer information about the water ice concentration at the poles of Mercury. And we use a technique that's called planetary neutron spectroscopy. And this is a technique that's been successfully used to measure hydrogen at the Moon, at Mars, and most recently at the asteroid Vesta as part of the Dawn mission. And what we do is we measure neutrons that are liberated off the surface of the planet by particles that are called galactic cosmic rays. And if I can have the first graphic, please. And cosmic rays, they're just very fast-moving protons that are flying throughout the solar system and the galaxy. And when they hit the surface of a planet like Mercury, they bust apart the atomic nuclei, and these nuclei contain neutrons. Can I have the next graphic? And so these neutrons, which are illustrated as the narrow yellow lines, they rattle around the surface, and some of them escape into space, at which time they can be detected by an instrument called a neutron spectrometer that's flying on board the Messenger spacecraft. Now, if you happen to have a situation where a crater, say at the North Pole, as illustrated in this graphic, contains water ice, can I have the next graphic? It turns out that, of course, water ice is H2O, so it contains lots of hydrogen. Well, the hydrogen in the water ice stops the neutrons very quickly. And so the telltale signature, almost in a unique way that you would have enhanced hydrogen, is a decrease in the number of measured neutrons that you would see as you're flying over the crater. And so that's what we're looking for, is a decrease in the number of measured neutrons to tell us that there's enhanced hydrogen. Now, in the next set of graphics, I'll give a few words about how it is that we make this measurement on the Messenger spacecraft. Can I have the next graphic? This is a perspective view of Mercury's North Pole, where we have these radar bright deposits discussed by Sean. And we can simulate what these would look like if you, say, put on neutron glasses, as it were. Can I have the next slide? And if your neutron glasses had perfect focus, this is the view that you would see. And again, where you have areas of enhanced hydrogen, you would see a decrease in the number of neutrons. Now, it turns out that planetary neutron spectrometers do not have perfect focus. They're, in fact, quite blurry. Can I have the next slide? This is what we would actually see when we're going over the Mercury's North Pole. We can't resolve individual craters spatially. Nonetheless, the telltale signature of hydrogen is still there if you have the enhanced hydrogen. And again, that's a decrease in the number of neutrons that you would see as you're flying over Mercury's North Pole. Now, what we can do is compare messenger neutron data with two hypotheses. And the two hypotheses are the following. One, that these radar bright regions contain very little to no water ice. The second hypothesis is that they are filled with water ice. Can I have the next graphic, please? And so what this shows is a plot of simulated neutron behavior, where on the vertical axis we have a quantity called relative flux. This is just a fancy name for number of neutrons that you detect. For different latitudes that you would make the measurement at. And the latitude is shown on the horizontal axis, and the North Pole is towards the right. Now, the little to no water ice hypothesis is shown in the white line. And what you see is that the neutrons would show very little variation as you go from the equator towards the North Pole. In contrast, the lots of ice hypothesis, filling up these regions with pure ice, would be shown in the blue line. And again, as you approach these radar bright regions, if they contain enhanced hydrogen, you would see decreases in the number of neutrons. Next slide, please. And so now what we've done is superimposed messenger neutron data on top of those two simulations. And what we see very clearly is that the data track extraordinarily nicely with the simulation that says we have enhanced hydrogen. And so from these data, we can conclude, number one, there is certainly an enhanced hydrogen abundances at Mercury's North Pole. Secondly, it quantitatively agrees with the amount of hydrogen you get if these radar bright regions are filled with water ice. Finally, when we combine this neutron information with other information such as the radar data, the areas of permanent shade, we have very compelling evidence that these regions are indeed filled with water ice. Now, in summary, we can ask the questions, how much is there? How much ice is there? And for this, we can combine both north and south poles because the situation in the south is very similar to the north. Well, it turns out if you add it all up, you have on the order of 100 billion to 1 trillion metric tons of ice. And the uncertainty on that number is just how deep it goes. We think it's at least 50 centimeters deep. It could be as deep as 20 meters. Now, of course, those numbers are big. It's hard to know what to do with them, so we can bring it down to Earth. And in fact, here in this town, if you take the amount of ice that we consider to be at Mercury right now, stack up the entire area of Washington, D.C. by about 2 to 2.5 miles of ice, that's what's present currently at Mercury's poles, according to our data. So these are very exciting results that we can sort of bring these all together, but there's more to come, and the next set of results are going to be given by Greg Newman with data from the Mercury Laser Altimeter. Thank you.
Thank you, David. If you take off your neutron glasses now and put on your infrared glasses, I will talk about the instrument, the Mercury Laser Altimeter, or MLA, also on Messenger. This instrument has been mapping the surface of Mercury and produced topographic maps. I'll show a movie, please, that illustrates how a laser altimeter operates. It shows a generic spacecraft orbiting a planet like Mercury or Mars or the Moon, and we've done this in those places. It fires a spear-like laser pulse to the surface using the energy of a flashlight, and it can record the distance to the surface by measuring the time that it takes for this pulse to bounce off the surface and then come back, usually less than 1/100th of a second. This measurement of time is so accurate that we can measure the distance to the thickness of one's hand, or the width of one's hand, and doing this 8 times a second, we build up a topographic map of the whole northern hemisphere. The next graphic, please, will show that it also measures the reflectance as a function of the outgoing versus the received energy. On the left, you see the laser pulse, just a few nanoseconds wide or billionths of a second wide, being fired at the surface of Mercury from Messenger spacecraft. And it hits a spot about the size of a house and then returns to the receiver telescope. You see the instrument on the right, and a few dozen photons are collected. Rather than count the individual photons, we transform them electronically into a waveform. And this waveform is measured at 2 different voltage thresholds, which gives us, with the times, 4 different points that we can use to estimate the area under the waveform as a triangle. And then we take the ratio of the received energy over the transmitted energy. That gives us the reflectance. The reflectivity of the polar regions can be done in complete darkness as well as in light because it's an active instrument. So the next slide will show the topography of the North Polar region, which we've now covered the surface of Mercury down to the equator with the laser altimeter. But in the North Polar region, we have very dense coverage up to the inclination of Messenger's orbit, and then with off-nadir observations, we can move even further towards the North Pole, shown by the arrows on the left. These observations are less clear, and some of them are, there are gaps where we haven't been able to obtain coverage yet, but we will. I want to draw your attention to the large crater colored in deep blue for the deepest shades, Prokofiev, in the center. This crater is the deepest location that we've measured yet on Mercury, and is, as you've seen in the previous slides, it contains radar bright deposits. The other craters as well that you see here largely are containers for radar bright deposits. The shaded relief shows you what the terrain looks like as if it were illuminated from the equator, and it shows that one wall of Prokofiev is in shadow and the other wall is in sunlight. We can use the accurate topography to determine what the illumination of Mercury is at any time of day, and make quantitative measurements of the solar illumination. The next movie will show, starting with Prokofiev in the center in complete darkness, the surface of Mercury. We've stretched the contrast here because it is so dark there that you wouldn't be able to see it on the television. Then as the movie sweeps through the Mercury solar day, you will see the crater Prokofiev. Could I have the movie, please? Crater Prokofiev in the center is briefly illuminated by the sun, and the area, the crescent-shaped area just inside the southern wall, remains in shadow. And as this repeats, you will see the sun illuminating all of these craters, but not illuminating the floors as it moves. This is a completely synthetic rendering, of course, but is quantitatively accurate. Now, with this illumination model, we can calculate, as the next speaker will describe, the temperature as well as the illumination conditions in the interior. So that area, Prokofiev, which is about the size of the impact crater that formed the mouth of the Chesapeake Bay, is one where we have the best MLA reflectance. And as you see in the graphic that we'll show next, the radar shows that this area is a crescent-shaped deposit of radar bright material, very large, and we were able to obtain profiles across it after about a year of orbiting Mercury. This Prokofiev crater deposit was our first real target of where we might see possible water ice. And indeed, as we go to the next graphic, we will show that this area is very interesting from the point of view of reflectivity. The map will show in gray the areas that we haven't covered. The average background reflectance of Mercury is shown as grayish white, and the red is the areas where the reflectivity is 2 to 4 times higher than the average background of Mercury. Now, we also show in dark the areas where the reflectance is at least twice as dark as the background of Mercury. So the two surprises were that, yes, we are seeing something that is as reflective as water ice, as seen in other laser altimeters in the infrared, and we're seeing it just exactly where the neutron spectrometers and the radar have also confirmed the existence of hydrogen and reflective material. So the real surprise, though, was that there were dark areas inside and surrounding any of the bright areas that we have seen. These dark areas were more pervasive than the radar bright areas, and we have an interpretation for these areas that they are a blanket that protects whatever bright volatiles lie underneath. So I will summarize these findings as saying the Mercury laser altimeter can see something which is extremely bright and coincides with all of the hypothesized ices that have been determined by other investigations. So now I'll turn it over to my colleague David Page, who will describe the thermal models and how this all fits together.
Thank you, Greg. The distribution of ices on planetary bodies is a very strong function of temperature. And in our science paper, we did the first detailed thermal model of the near surface and surface of Mercury based on the new messenger topography data. The first graphic shows some results from that model from the viewpoint of the North Polar region, in a region where we got the very best MLA, or Mercury laser altimeter topography data. Mercury, as it turns out, being the closest planet to the sun, has the widest range of temperatures of any planetary body in the solar system. At the equator, temperatures can get up to 700 degrees Kelvin during the middle of the day. And even at 80 degrees latitude, where you're seeing right here, annual maximum temperatures get up to about 550 Kelvin. However, when you get into the permanently shadowed areas, our models tell us that the temperatures can dip down to as low as 50 Kelvin. That's 50 degrees Celsius above absolute zero, which is as cold as you can possibly get. The thermal model also has the capability to tell us exactly where on the surface and below the surface different types of volatile materials ought to be stable. And the next graphic shows our results showing the stability regions for water ice on the surface and subsurface of Mercury. The gray regions show areas that are too warm to ever have ice being stable. The colored areas show where below the surface Mercury would have temperatures that are conducive to water ice stability, whereas on the surface in these colored areas, it's too warm for water ice to be stable. And then in this particular region, there are a few areas where we color those white. Those are areas where water ice would be stable directly on the surface. What we did in our paper was we compared the regions that we calculate to be water ice stable with the areas that have been shown to be radar bright, and we basically obtained a perfect match. which means that the areas that, the reason why the regions are radar bright is because they in fact are composed dominantly of water ice. The next graphic shows the MLA, or Mercury laser altimeter reflectivity measurements for these various same areas. And you can see very clearly these dark regions that are associated with these impact craters. When we first saw these measurements, we started racking our brains about what could this mysterious dark material be. We know basically two things about them. One is that they're dark. In fact, they're very dark. This material has the same reflectance as a lump of coal would be. The second thing we know about them is that they are hanging out in these cool regions, regions that have temperatures sort of less than the boiling point of water. When we look around the solar system for materials that match this description, the main type of material that shows up, in our minds at least, is the concept that these are dark, organic, rich deposits. When we look at comets or we look at icy bodies in the outer solar system, we often find that these objects are extremely dark, and spectroscopically we know that they are covered by this dark, complex organic mix of materials. This material, we believe, therefore, is also being deposited on Mercury by these same types of objects, and this organic material may be the same type of organic material that ultimately gave rise to life on Earth originally. If you look at the graphic a little more carefully, and the next slide shows that, the interiors of some of these dark regions actually contain brighter material. And the question is, what could this material be? If you look very closely at the locations of these spots and then go to the next graphic, we show what the thermal model predicts in these particular areas. And you can see that all of these bright areas, both in their geographic extent and their size, show up as surface ice deposits in the thermal model results. And this was very gratifying for us because it means that we're definitely on the right track when we're saying that these deposits are made out of water ice, because there's an exact match between the MLA bright areas and the surface water ices that are predicted by the model. The next graphic describes our general concept for how the Mercury polar deposits got to be the way they are. The craters at the high latitudes are illuminated obliquely by the sun. The equator-facing walls are very, very hot. As you move towards the poleward-facing walls, they are in permanent shadow and are very, very cold. So there's an extreme thermal environment within each of these craters. The next slide shows that there is a source of water and a range of other volatiles from objects impacting Mercury, as indicated by this comet here. This material can hit at any latitude on Mercury, and then the volatiles migrate about the planet, and eventually, as shown in the next slide, some fraction of them wind up in the polar regions as a heterogeneous mix of materials. Over time, there is a migration of water ice from areas that are warmer into areas that are colder, as shown in the next slide. And this tends to concentrate the contaminants that were present in the water ice near the surface, forming essentially a lag deposit. Over time, as shown in the last slide, this material darkens after exposure to the Mercury space environment, and we end up with the situation that we currently have. Dark deposits that cover the permanently shadowed regions, underlain by water ice deposits, and then finally, in the very coldest places, water ice deposits exposed on the surface. Now, the most interesting thing about these deposits is that they appear to be in a very organized state. In other words, we find water ice exposed everywhere that it's cold enough for it to be, and we find subsurface water ice every place that it's cold enough for that to be. For this situation to occur, it cannot be the product of something that happened, let's say, billions of years ago in the ancient past, but rather some process on Mercury that is both delivering as well as redistributing these volatile materials and placing them in places that are thermally stable. With that, I'll turn it over to Sean Solomon for some concluding remarks.
Let me take just a couple of minutes to tie together what you've heard here today. One of the major objectives of the Messenger mission when we were selected and when we launched was to test the idea more than 20 years old that the polar deposits on Mercury discovered by Earth-based radar consist dominantly of water ice. They match the radar characteristics, and we subjected that hypothesis to 3 very stringent tests. Does it have the neutron spectrometry signal that you would expect for water ice? As you heard from David Lawrence, yes, it does. Does it have the near-infrared reflectance, where exposed at the surface, that you would expect for water ice? As you heard from Greg Newman, yes, it does. And finally, does it match the very detailed thermal models that we can now construct on the basis of messenger measurements of the topography of the North Polar region of Mercury, and match that to the thermodynamic characteristics of water ice? And you heard from David Page, the answer is yes, it does. So water ice passed these 3 challenging tests, and in fact, we know of no other compound that matches the radar, the neutron, the reflectance, and the thermal characteristics that we have documented with the MESSENGER spacecraft. So the hypothesis that these deposits are dominantly water ice with an interesting darker component covering them has survived these very challenging tests. So most broadly, let me conclude by saying that MESSENGER has revealed a very important chapter in the story of how water ice and other volatile materials have been delivered to the inner planets, including Mercury. We think by the impact of comets over time and volatile-rich asteroids. It's extraordinary that this chapter is so well preserved on the planet closest to the sun. And that is the result of the extreme stability of the cold temperatures in Mercury's permanently shadowed regions that are stabilized by the also extraordinarily stable spin state of the innermost planet, which is in a spin-orbit resonance and an orbit that favors the stability of these deep cold traps. So in the broadest sense, this chapter, read on Mercury, and one which we on the MESSENGER team hope to pursue in greater detail over the months ahead, is telling us about the delivery of water and the delivery of some of the complex organic building blocks on our own planet. And it behooves us to understand this particular chapter on the innermost planet as well as we can. Thank you, Dwayne.
Well, thank you. Okay, now we're going to open up for questions, and we're going to do something a little different here this afternoon. Clearly, this is a media briefing. The media have a lot of their stories already, but we also have a tremendous opportunity to directly talk to the public via social media, Twitter, Facebook, Google+. And NASA has a tremendous following, and they're following the conversation. And again, join the conversation at #AskNASA. So we're going to take questions directly from the public. I'm also being told that we have lots of students watching this, the young folks. And I've jotted down some of the questions, a couple of them for you, Sean, and the team, and one for Jim Green, and we'll start there. And then if we have any media on the phone, we'll go to them. So we're going to go directly to the public here. Let me start with the first one here for you, Sean. What's next for the mission?
Well, we've got a very broad menu of targeted high-resolution observations. We certainly want to follow up on what you heard about today, the North Polar regions and the bright deposits, the dark deposits, what they mean, what the images we can acquire of the areas just adjacent to those regions in permanent shadow, whether there are any chemical or morphological signatures of unusual phenomena there. But Mercury displays a host of very interesting phenomena that we have been talking about and writing about for a year and a half. Its magnetic field, its extraordinarily dynamic atmosphere, its wonderfully complex geological history, some of which has a record of the loss of volatile materials to space, creating landforms that are seen on Mercury and not seen elsewhere. We want to understand the chemical and the geological origins of those features. So we've got a long menu of detailed observations that we're planning over the next several months. We hope to continue observations well into next year. Next year will mark solar maximum, the maximum in the activity of the sun that follows an 11-year cycle. Because Mercury is the planet closest to the sun, it is also the most dynamic planet in its response to changes in solar activity, to solar storms, to the streams of energetic particles that are thrown out from the sun, to the extremes of radiation that are thrown out from the sun during many of these storms. So Mercury has a front row seat, and as long as MESSENGER is taking data, MESSENGER will have a front row seat as well. So stay tuned. There are a lot of new observations to come.
And we're going to continue taking questions from our social media. And again, join the conversation, Twitter, Google+, Facebook, and others at Twitter, #AskNASA. And we'll get to the phone lines to the media, but again, we're going to let the public and the students directly talk to these, the MESSENGER team and their incredible work they're doing. So, Sean, and for the team member, here's a fun one here. How would you describe, is this a period or an exclamation point on the finding? And if there's water ice, what does this say about life in the solar system? Where there's water, they say there may be life.
This is a good question for Jim Green.
Oh, it's a
Well,
question
my
about punctuation.
answer to that would be,
You want to,
the more we examine the solar system, the more we realize it's a soggy place. And that's really quite exciting, because that means the amount of water that we have here on Earth that was not only inherent when it was originally formed, but probably brought here, that water and other volatiles were brought to many other places in the solar system. So it really bodes well for us to continue on the exploration following the water and its signs throughout the solar system.
To answer the first question, my own choice for punctuation mark on the story today would be an exclamation point. But I'll ask my colleagues to add.
We would all agree, if not only for the exciting results, the amount of work that was put into this in terms of the effort of so many people on the MESSENGER project, not only putting the instruments together, but doing the analysis. It's an absolute exclamation point with the excitement that we have of being able to have these results. And as Sean said, they're difficult, challenging results, and to have them all come together in this way, I was using an analogy earlier, it's kind of like a key that you get the right key, it gets into the lock, it turns, and the door opens. And all the results are pointing to the same place, and that's definitely an exclamation point.
Yeah, I'll vote for exclamation point. We never expected to see this new wrinkle of dark, organic-rich materials in places where we were looking for water ice. That was astounding, and we didn't expect the results to be so clear, but the thermal models certainly made them an explanation.
Yeah, it's very rare we get such good agreement between data and models, so we'll take this one.
Let me be clear, no one is saying that there is life on Mercury. Nonetheless, the history of life begins with the delivery to some home object of water and of the building blocks, the organic building blocks, that must undergo some kind of chemistry, which we still don't understand on our own planet. And so to capture the early phases of these processes on another solar system body gives us a window into the importance of these early processes even on our own planet. And so Mercury is becoming an object of astrobiological interest, where it wasn't much of one before. That's not to say that we expect to find any life forms. I don't think anybody on this table does. But in terms of the book of life, there are some early chapters, and Mercury may indeed inform us about what's in those chapters.
Sean, I'm glad you explained that, because on the Twitter, you just answered about 30 questions. Life and water. So let me toss this question to Dr. Green. Dr. Green, you have had a lot of successes, your division. Mars missions, GRAIL, Cassini, of course, MESSENGER. What is your recipe for success?
Well, Working with the community has just been a really delight. The scientific community has matured over the years. They're well-focused. They're dedicated. We have a cadre of engineers that are just tremendously supportive. Combine that with the expertise that have been developed at our centers, and it's a winning combination. It's very hard to do these missions on time and on schedule, but we have a couple things going for us. One is a planetary window, and that's a blessing and a curse. The blessing part of it is we've got to get things done, enabled to be launched on time and in that window. The curse is, it's a big problem financially if we miss it. So we all are dedicated to work very hard to be able to meet those planetary windows, and because of that, the program indeed has been quite successful over the years.
Before I ask the next question, I want, before we end here, I've got, looks like classrooms from the Midwest, but they want me to ask each of you to explain how did you get into your respective field and any advice you can have for students. But we'll say that for last because we're going to go right down the line. But the next question, in shadowed icy areas, could it be that around the fringes of the ice, there exist conditions that are right for liquid water?
I can take that question. There are certainly temperatures that are conducive to liquid water, but the problem with Mercury is it doesn't have an atmosphere. So if you could create a little puddle of liquid water in these areas, the molecules of water would evaporate off and fly off in all directions, and eventually, very rapidly, in fact, you would have no more liquid water. So while you could have metastable liquid water, it wouldn't be like a pond or a wet, soggy subsurface area at all at Mercury. It would just turn to ice or turn into vapor. There'd be no liquid.
Okay, again, I want to thank you all for joining the conversation here. Ask NASA, the hashtag Ask NASA, join the conversation, Twitter, Google+, Facebook. And the next question, let's see, does the measurement method used by Messenger to detect hydrogen allow the determination of isotopic distribution of hydrogen?
No. Basically, no, that's the answer, but we're measuring hydrogen atoms, and that's what we're able to tell. We can't get into those type of details of isotopes. And so it's really it's a basic story of billiard ball physics, and what we measure is neutrons when they hit a hydrogen atom, just like when you're playing billiards, and the cue ball dies when you get a dead-on hit. And that's what we're measuring, and we count neutrons, and when there's not as many of them, that's the signature of hydrogen.
Sean, I think you answered this, is that, so we keep discovering new places that seem to hold water. Can we now say that water is actually quite common in the solar system? Did you? Jim, you want to?
I didn't answer that directly, but the most likely source for the polar deposits, which have passed all the tests for a composition that's dominantly water ice, the most likely source for that water is actually pretty far from Mercury. It is the source region of comets and ice and volatile-rich asteroids, namely the outer solar system. And so water is indeed a common component of our solar system. That's a big component of the ice giant planets. It covers many of the satellites of the major planets, and it is expected to be a constituent of many of the small objects that are in the outer solar system beyond the main asteroid belt and extending out beyond the orbit of the most distant planet. So there's a lot of water out there, as there is a lot of water around other stars, but at substantial distance. And what these observations at Mercury tell us, and what our own thinking about the Earth has made us imagine before, there are mechanisms for perturbing the orbits of comets and asteroids that have operated over the entire history of the solar system. And so the history of water on our planet and the history of water ice on Mercury are very much also the history of interactions of comets and asteroids with the inner solar system. So there is water in the inner solar system, and we experience here on this planet often. But a lot of our water, we now suspect, just as the material that's likely to be water ice on Mercury, originated at a different part of the solar system.
Okay, I want to tell our audience out there, and thank you for sending in questions and joining the conversation, hashtag Ask NASA. We are going to do a couple of more questions, and then I promised the students that are watching that you would hear from the individuals on how they got started in this and any personal recommendations on guidance. But this question is for Dr. Green. Jim, does NASA have plans for a Mercury lander anytime soon?
That's a good question. Landing on Mercury and actually tasting the water, that would be the confirmation of what we would seek in the next step of doing this. Would be an incredibly difficult, but an incredibly exciting mission. We have opportunities for the community to be able to consider that, plan, and build that through a competitive process, and that, once again, would be our discovery program. So perhaps the student that put in that question would be in line in later years to be part of that team, and let's hope so.
Okay, so I'm going to use this time for the students. Jim, since the camera's on you, just how did you get involved in your field, and any guidance for not just middle school students, but we have lots of high school students watching also?
Well, I grew up, of course, in the Apollo era and the early Star Trek, and so there was quite a bit of interest in space. But what really got me started turns out to be in high school, when I had an opportunity to look through a telescope and actually get involved in being part of an observatory. And that was just tremendously exciting. I built instruments for the telescope that I used, which was a 12-inch Alvin Clark refractor. And so when I left high school, I knew exactly what I wanted to do, and that was to get a degree in astronomy. So I went to the University of Iowa, and at that time they were on their 54th instrument on a spacecraft, and I thought, this is absolutely fantastic to do astronomy from spacecraft. What a great idea, and I just got into the space field from that. But what it does take to be able to hang in there and get your degree and follow through and become a PhD, get your PhD in that respect. Not only is an interest and drive for mathematics and a love of the science, but it really takes determination. I can't underestimate how important determination has been in my career to be able to get me to the next step.
Sean?
I started out as an earth scientist, as a student of our own planet, using geophysical tools like seismology. When I was an undergraduate, the very first spacecraft to send images back from another planet did so, and I happened to be at an institution where the images were shown in real time as they were received. And in those days, it showed up on a video screen one line at a time. It's very, very slow, but one line at a time, the cratered surface of the ancient southern uplands of Mars were revealed by just a handful of images that were sent back by the Mariner 4 spacecraft. But that was a captivating event for me. And so even though I remained an earth scientist, when the opportunity to work on planetary missions came along at different stages in my career, I was eager to join in. David?
Okay, well, as with you, Jim, I'm grew up excited by Apollo, but I'm a bit younger than you, so I was a young kid for Apollo 17. But at the time, that was still very exciting. I wanted to grow up and be an astronaut. But unfortunately, my eyes are kind of blurry like the neutrons, and so that's not a possibility. And so talking to people, they said, go into science, go into physics. And so I went into physics, and the astronaut thing didn't work out, and I think my wife is probably pretty happy about that. But doing the science has been very exciting, and having this privilege to be part of some of these missions. I helped out with some of the early, the Lunar Prospector mission, and trying to be in the right place at the right time. And as you said, determination, I would say perseverance. There's a lot of steps where it doesn't go right, and you just keep pushing forward, and good things often happen. So that's the advice, keep persevering.
Well, I got my degree in mathematics, undergraduate degree, and mathematics remains the queen of the sciences. I benefited greatly from the Cold War and the competition and the emphasis on science, technology, and mathematics education that resulted, which I'm hoping that others will benefit from in the future. After a few detours, I became, as did Sean, an earth scientist looking at the bottom of the oceans of the Earth. Did my PhD degree on marine geophysics using sonar and gravity and other geophysical techniques, magnetometry, to understand the motion of the Earth's crust and how it forms. I guess with the Clementine mission and the Mars Observer and Mars Global Surveyor missions providing me the opportunity to use lasers instead of sonar, I became a planetary scientist. But it was very hard to resist the thrill of being able to make the first observations of a body outside of the Earth with lasers and make maps, and the rest has kind of fallen into place until now it's full circle. We're measuring water on Mercury.
Thanks. My association with NASA started very early. I was selected as part of a national competition to fly a student experiment on the Convair 990, which was a jet aircraft that was run by NASA Ames. And I designed an experiment and then got to fly to NASA Ames and got to fly on this Convair 990 around the North Polar region of the Earth, as it turns out. We went to Alaska and to Greenland. It even flew over the North Pole. And this aircraft flew at about 1,000 feet the entire time, elevation, with all kinds of remote sensing instruments, getting radar, getting laser altimetry, and every type of remote sensing instrument you can get. And for me to be able to hang out with the scientists, to experience this as a high school student, was easily the most exciting experience I've ever had in my life, both before or after. And here I am, looking at the ice on Mercury. I wouldn't have thought it at the time, but I guess I've never stopped. So I'm really grateful to the opportunity that was provided by NASA Ames, and Mike Donahoe, I guess, was the name of the guy who ran the educational program there. But yeah, it was great.
Okay, what we're going to do is we're going to end here. Again, for the folks who are on Twitter and Google Plus and Facebook, the conversation does not stop here. Join the conversation, particularly on Twitter at #AskNASA. We'll continue to answer your questions. And for the media who are on the phone line or watching this, the individuals will be available for interviews following this. Contact myself or my colleague, Paulette Campbell, at APL. Again, I want to congratulate the Messenger team. You can get the information and the latest images and other science information on www.nasa.gov/messenger. Thanks for joining us. Have a great day.